Hello, my name is Michael Mu, and I will be presenting our work in self-supervised distilled learning for multimodal misinformation identification. Misinformation has gained increased attention as it continues to spread on social media. For example, Weibo reported nearly 76,000 different instances of misinformation in 2020. We will be focusing on one form of misinformation, colloquially called deepfakes. Deepfakes are created by repurposing existing imagery in new context with false captions. They're easy to create but difficult to identify. They require the ability to recognize both visual and textual information, as well as compare the underlying meanings. For example, here we must identify Novak Djokovic in the caption and picture and understand they are the same. We decided to evaluate our model on news clippings, a dataset created using automation on news articles. This dataset was created using 4 different methods to create 5 subsets. The first 2 splits used a clip model to match captions and images based on their embedding similarities. The third split identified named entities and matched captions with them in a different situation. The fourth split used ResNet to match similar looking scenes from different locations, and the last split is a combination of all 4 in similar numbers. Our approach involves 2 parts, pre-training the embeddings and training the classifier. For pre-training, we augment the loss function with self-supervised learning. For classification, we augment the training with knowledge distillation. To augment the pre-training, we take the initial input and perform a series of transformations with different values to generate 2 slightly different inputs. The embeddings generated from these altered inputs are then trained to be as similar as possible. For classification, we used KL divergence to train the student network to approximate the teacher network as an additional term to the classification loss. We evaluated the performance of the base model, then added self-supervised learning and the knowledge distillation. The first experiment shows the performance of a clip model with a vision transformer. We can see generally each augmentation shows improvement. The next experiment shows the performance with a ResNet image encoder. ResNet has better performance, and we again see improvement with augmentations. This experiment compares the performance of models if they are trained on only one subset of the dataset. We find our model performs better than base clip in 3 categories. It should be noted that the categories that clip performed better at were also the ones created using the same clip model. We also conducted a data scarcity experiment as an evaluation of the self-supervised learning augmentation. We found our visual transformer model achieved performance parity with only half the training data, and our ResNet model achieved performance parity with 3/4 the data. We conducted experiments to evaluate the best training strategy. We tested freezing the entire model, or the last few layers, or fine-tuning the entire model. Unsurprisingly, fine-tuning the entire model performed best. However, we noticed that fine-tuning the last few layers performed much worse than expected. Finally, we present some qualitative examples from our model. In these examples, the green region contributed as a falsified prediction, and the red regions contributed to an unfalsified prediction. In conclusion, we found that self-supervised learning generally improved performance and showed promise in data-scarce conditions. We found knowledge distillation effectively improved performance. And lastly, we found that fine-tuning the entire model had the most effective performance. Thank you for listening.